see my full screen?
Yep, absolutely, Doctor. Okay, great.
Okay, excellent. First of all, thank you so much for the very kind invitation. It's a pleasure being here virtually, at least, and it's a great pleasure to speak at your conference, which the lineup is amazing. So I'm happy to participate. So I'm going to talk about organic materials for bioelectronic applications. And to give you a brief introduction, I know it's maybe a little bit different topic from some of the many other talks of this conference. Organic bioelectronics is sort of the marriage between organic electronics and a biological system in one way or the other. So we're interested in converting biological signals into electrical signals, or the other way around. To be able to do that, we need organic electronic materials that can function, that can operate in aqueous media. And we need organic materials that have mixed conduction properties, meaning that they can both conduct ionic charges and electronic charges in the solid state. Here are some examples of let me just find my pointer, sorry. Here are some examples of some applications. There's lots of different applications of organic bioelectronics. Here's some research from researchers in Linköping, Sweden, where they built an organic electronic ion pump that can deliver a neurotransmitter such as GABA at the spinal cord, very, very localized delivery of drugs with an organic electronic ion pump. Another example is the development of artificial synapses, again using organic bioelectronic materials. And a last example I wanted to highlight is research from KAUST in Saudi Arabia, where they built a glucose sensor that's self-powered by an enzymatic fuel cell, so sort of a dual device that can power itself from the fuel cell and at the same time function as a glucose sensor. So just to give you a flavor of some of the applications that people are preparing for in the context of organic bioelectronics. In my group, we're more interested in developing new materials and understanding the properties, the structure-property relations of these new materials. And the main device we use to assess new materials is the organic electrochemical transistor. So I'll spend a few minutes talking about that. And of course, the interesting aspect of this type of transistor is that it operates through a mechanism where we have mixed conduction of ionic and electronic charges. In a similar fashion to a field effect transistor, it has 3 electrodes, but the important thing now is that it's gated electrochemically through an aqueous electrolyte rather than a solid dielectric, as we know from a field effect transistor. And that means that it can operate in aqueous media, and you can use it to amplify biological signals. Similar to a field effect transistor, it can work in accumulation or depletion mode, depending on the type of material. And quite importantly, the performance scales with the thickness. So we can tune the performance by tuning the area, the volume of the active material, which is the organic semiconductor. And as I said, we have both ions and electronic charges playing a role in the charge in the transport in the bulk film. Because we're interested in using these materials as sensors, we're quite interested in the transconductance, GM, which is the change in drain current over the change in gate voltage. You want a high change in drain current with a relatively low change in gate voltage to get a good signal from your biosensor. If we look at the equation for the transconductance, we can separate out the mobility mu, as the electronic mobility, and C star, the effective capacitance. Those 2 parameters are the only ones that are related to the material, to the active material. The other ones are related to the configuration of the device and to the way we operate it in terms of bias. So only mu and C star are materials dependent. So we think about the mu C star product as the materials figure of merit, one we can understand in terms of new materials that we develop. And if we look a little bit more carefully at the operating mechanism of these types of transistors, you might be more familiar with the organic field effect transistor, which I've shown here on the left, where you have a solid dielectric, and how that operates is that you only build up a small accumulation layer between the dielectric, at the interface between the dielectric and the semiconductor, and all the charge transport takes place in a few monolayers very close to the dielectric. It's very different in the organic electrochemical transistor, where we have from the aqueous electrolyte that takes the role of the dielectric, we have these mobile ions that can penetrate into the bulk of the organic semiconductor. So we have a completely different mechanism where the bulk film plays a role in the charge transport, and we have mobile carriers throughout the entire film, and both ionic and electronic transport in the bulk film. Of course, that poses a question: how can we design materials that can facilitate the incorporation of ions into the bulk semiconductor film, which is not something we would expect from normal organic electronic materials. So if we look at a typical field effect transistor material, can be these types of polythiophene here, where we have a conjugated backbone that can delocalize pi electrons, meaning that we can inject charges, either positive charges, electron holes, or negative charges, electrons, into the material, and then we have efficient charge transport along the polymer backbone, and we have efficient charge transport when the polymer chains pack together, so charges can also hop from one polymer chain to the next. So these types of materials are very good for electronic transport at the interface. And these alkyl chains, the blue chains here, the aliphatic chains, we add them onto the polymer backbone to make the material solution processable, so we can make inks of these materials, and we can spin coat, we can print thin films of these materials for large-scale production of these materials. So taking that as a starting point, that's sort of my background. So we were thinking along the same lines: how can we modify these materials to then work in an organic electrochemical transistor? And what we came up with was substituting these alkyl chains, the aliphatic chains, for solubility. We decided to make them much more polar, so we added these ethylene glycol chains rather than the alkyl chains onto the polymer backbone. These much more hydrophilic and polar side chains, we were hoping that they would facilitate ionic transport in the film, in the bulk film. So allow the material to swell in water, and then the ions can move in and out of the film. That turns out to work quite well, actually. Here's a cartoon of where we compared two different polymers. The one I showed on the left before, where we just have the polymer backbone and aliphatic side chains. We can see we get an OFED type operation, where we only get charge accumulation at the interface between the electrolyte and the semiconductor film, and the effective capacitance is quite low. We don't see much increase in the capacitance as we increase the bias. On the other hand, if we decorate the polymer with these very polar side chains, now we see that the ions enter into the bulk of the film, and we can dope the entire polymer film, which is, of course, important for generating lots of charge carriers. And we see that in the effective capacitance, once we apply a small bias to sort of force the ions to go into the film, we see a 2 to 3 order of magnitude increase in the effective capacitance, telling us that this cartoon here is a nice representation of what's going on. We get bulk doping of the film due to these ions entering into the film and compensating the electronic charges that we build up with the bias. So that turns out to be a quite nice materials design criteria for making these mixed conduction organic semiconductors. And we we made several families of these types of materials, and we see that they work quite nicely. I won't go too much into details about this plot here, but on the y-axis, we have the transconductance that I talked about before as a figure of merit for the sensing capabilities. And on the x-axis, we have the dimensions of the organic, of the active layer, which I also mentioned plays a role. So we need to compare, when we compare materials, we need to compare them across the same dimensions of the active material. But you can see here at the top, at high transconductance values, we have these new materials here, these polythiophene with polar side chains to be developed, and they perform very, very well. In the black stars data points here are from one of the conventional P-dot materials that people before then used to use as the benchmark material for mixed conduction. And you can see our new materials here outperform the benchmark P-dot PSS material in all dimensions, more or less. So this materials design rule about adding these ethylene glycol chains onto the material is sort of emerging as a universal way of introducing mixed conduction in these materials. I've also listed the mu-C star products that I talked about in the beginning to give you an idea about what a good value is in terms of the mu-C star product. For this polymer here with a thiophene comonomer, we get a value of 167 farad per centimeter per volt per second, and slightly better performing when we have a thienothiophene, a more conjugated extended unit, we get a mu-C star product of 261. So try and keep these numbers in mind as we'll talk about some new materials and see how they compare to these sort of new benchmark materials that we have developed. So moving forward from these initial materials, we made these with a chemical polymerization technique called a Stille polymerization, which is a very efficient way of making pi-conjugated polymers, but it's also quite toxic. We use these organotin reagents that are not particularly nice to work with. So we wanted to sort of develop a more green synthetic approach and improve the process of making these materials. And this process here is called the direct arylation polymerization, where we avoid these organotin reagents and we get a direct coupling between the aromatic system here, just with hydrogens in the active positions, and a dibromide, a thiophene dibromide as the coupling partner. And that we showed that works quite nicely, so we can surpass the use of organotin reagents. And we made this new, again, glycolated polymer here to investigate for mixed conduction properties and eventually bioelectronic applications. What happens when we introduce, in addition to sort of looking at making a more green polymerization process, we also introduced this tetrafluorobenzene unit into the polymer chain. That's a very electron withdrawing and electron deficient unit. And that means that the frontier energy levels, the HOMO and the LUMO, they get much lower in energy compared to the benchmark material. So for example, the HOMO, which is important for charge injection into the material, reduces from minus 4.4 electron volts for the benchmark material down to minus 5.1 for this new material with the tetrafluorobenzene. That has significant effects on the operation of the OECT device. On the left here, we see the transconductance in the solid line as a function of the gate voltage for the benchmark material. And we can see we get a peak transconductance at a relatively low gate bias around minus 0.4 volts, meaning that we can operate this OECT device, this biosensor, at low bias, where we don't need to worry too much about side reactions from the high bias. Our new material with the tetrafluorobenzene, due to the much lower HOMO level, the increased ionization potential. We need to bias the material higher to get a peak transconductance. So we need to apply a higher bias to get this sensor to work. And also we see a significantly lower mu-c star product, at least an order of magnitude lower. The lower HOMO value does mean that we have better ambient stability. It's less likely to react in an oxidative way with ambient species such as oxygen and water, but there's definitely room for improvement in terms of the performance and also the energy levels. So we have started some work looking into this, and instead of the tetrafluorobenzene units, here we have introduced a more electron-rich component, which is a dialkoxybenzene, and we can see that has a significant effect on the HOMO value. We bring it back up again due to these electron-rich components here now, and also the mu-c star product is increased at least 4 or 5-fold. So we have a whole family of polymers in this class here where we are starting to be able to tune the energetics, and we'll be able to tune the performance in terms of the mu-c star product. So that's one promising way of taking these materials. I'm going to move on to some other classes of materials. So I just wanted to summarize briefly on this type of system here. We're doing some work, and you can see that this additional phenylene unit that we introduce into the polymer chain, we can use that as a tool to change the frontier energy levels, to change the polymer backbone planarity, which is quite important for charge transport, and also to tune the solubility, which is important for solution processing. We're also looking into, in this case here, you can see we have the ethylene glycol chain on a specific position of this thiophene. In principle, we could also change it onto the other position of the thiophene over here, this free position here, and that has some significant influences on the performance as well. So we're studying that in detail as well. And on the way that the polymers pack, again, which is important for the charge transport and the ionic transport. And finally, of course, we can modify the co-monomer unit that we choose to polymerize with. We saw an example of a thiophene. We can use thienothiophene and phenylene. So again, we're making more detailed studies to understand the role of the co-monomer units. I'm going to change gears and talk a little bit about small molecule mixed conductors. If you're familiar with the organic field effect transistor literature, there's many examples of small molecules rather than polymers working particularly well in field effect transistors. And this is just one example from Xian and Bao's group some years ago, where they achieved very high mobilities for small molecule systems. So we wanted to do something similar for these mixed conduction systems here. And I'll quickly go through the sort of design considerations that we took. So we started with this phenylene, thiophene, phenylene small molecule here called PTTP. And this is a well-known material when you have the hexyl side chains, the C6 aliphatic side chains on the system, been developed back in 2003 by Toby and Mark's group. So we wanted to, again, use the same trick of substituting these alkyl side chains with ethylene glycol side chains. And you can see here in the cyclic voltammograms conducted in aqueous electrolyte, the original material does not switch. We cannot electrochemically switch that in aqueous electrolyte. In agreement with our previous studies, we only get sort of accumulation of charges at the surface. But when we make it much more hydrophilic, much more polar, we can see the ions penetrating into the bulk of the film, and now we can do an electrochemical switching of this material in aqueous electrolyte. Although we still need to apply quite a high bias, you can see the onset of oxidation is above 1 volt, which is quite high, and it's not particularly favorable for organic bioelectronic applications. So the next thing we did from a synthetic point of view was to try and make this material much more electron rich, so we can oxidize it at a lower potential. We decided to modify these two central thiophene units here and turn them into E dot, this ethylene dioxythiophene unit here. So when you take the two central thiophene units and substitute with a central bis E dot unit, you get this molecule here, and you can see now the cyclic voltammetry of a thin film in aqueous electrolyte. It switches very nicely. We have a very well-defined oxidation wave, and again, when we come back, we have a very well-defined reduction peak. So it's a very reversible process in the solid state in aqueous electrolyte, and you can see the oxidation potential has decreased quite significantly compared to the thiophene derivative above, which is all good indications of mixed conduction in the solid state and potentially a good OECT material. Nevertheless, when we did some structural characterizations of this material, we saw that it was extremely crystalline. We managed to get a single crystal structure of the small molecule. And when we look carefully at the single crystal structure, we don't see any close pi-pi interactions, meaning that the charge transport in this crystal is probably not very good. And that actually explains why we struggle very much to get working OECT devices for this material. So therefore, we went back to the synthetic chemistry lab. Oh, I should mention, we also struggle a lot to get homogeneous films of this material because of the high crystallinity. So the printing process is not very efficient. So we went back to the chemistry lab and tried to see if we could address this from a synthetic chemistry point of view. And what we did was elongate the pi conjugated segment of the molecule. So rather than having two E dots in the middle, we extended the system to having 4 E dots. And also, rather than 1 phenylene unit on either side, we extended to 2 phenylene units. So we made this molecule here, which has a much longer pi conjugated segment, and hopefully better charge transport properties and better film formation properties. And you can see here in the GWAX, in the X-ray, it's much more polymer-like. It's not as crystalline as the other small molecules, so that's a good thing. When we do thin film spectroelectrochemistry, so we look at the optical properties as we apply a potential, we can see that we get a bleaching of the neutral state, and we get, first we generate a polaron species, so a radical cation shown here in green, and when we increase the potential further, we get a dication, we get a bipolaronic species. So we do see the generation of charge carriers, which is promising. And again, in the thin film cyclic voltammetry experiment, we see nice and reversible oxidative behavior, again forming the radical cation, the polaron species, and subsequently the dication, the bipolaronic species. Another thing we observed was that when we blend in a PEO, sort of a passive polymer matrix, we see much higher current responses, we see better film formation properties. So that turned out to be a key in getting good OECT devices for this material. So we blend in 10 weight% high molecular weight polyethylene oxide, and then we get good working OECT devices. The output characteristics are shown here for the OECT. We still get a very small μc star product, around 1 farad per centimeter per volt second, but as the first working OECT device with a small molecule semiconductor, I still think it's a quite nice result, but there's definitely room for improvement. I'm going to spend the last few minutes talking briefly about another system that we're starting to develop. Again, coming back to the polymers, and we're looking into this iso indigo scaffold here, which is a very nice polymer backbone from a synthetic point of view. There's a lot of things you can tune chemically. So we have started with this iso indigo here. There's lots of steric hindrance in this system, indicated here by the gray curved ellipsoids. So we've done some structural modifications to get a more planar polymer backbone. One is the thieno iso indigo shown here, and the other one is the acer isoindigo, where we've substituted one of the carbons with a nitrogen. In both cases, you get much more planar polymer backbones. And these two systems have dramatically different optical properties. The thieno isoindigo, here polymerized with an electron-deficient benzothiodiazole, has a very narrow optical band gap. You can see the absorption is out in the near IR, whereas the acer isoindigo, again polymerized with the same benzothiodiazole, absorbs around 600 to 700 nanometers, so in the visible part of the spectrum, and has a much wider optical band gap. So that's summarized here. The energy levels are quite different for these two materials. The acer isoindigo with the benzothiodiazole has a very low-lying LUMO level, which is good for electron injection into the material, meaning that it's a potentially a good N-type material, so transport of electrons. And the thieno isoindigo derivative has a very high-lying HOMO, making a good candidate for P-type charge transport, so injection of positive charges into the material. We see that in the thin film spectroelectrochemistry. I'll go over this quickly, but when we do reduction of the acer isoindigo, we see a bleaching of the neutral state, and we see some indication of a negative polaron forming when we reduce this material. Similarly, when we oxidize the P-type candidate, we see a bleaching of the neutral, and we see the beginning of polarons forming out here in the near IR. So the spectroelectrochemistry in aqueous electrolyte is promising for this mixed conduction properties that I've been talking about today. And it does turn out that these are indeed efficient OECT materials. The N-type candidate does give an N-type response in the OECT, and the P-type gives a nice P-type response in the OECT. We have a manuscript submitted. Hopefully it will come online soon, early in the new year. So to conclude, I think my time is running out. Here's some of the stories that I've talked about. We have developed some small molecule mixed conductors, where we've shown how the chemical modification of the high conjugated backbone is important to tune the properties. We're starting to work on this new series of P-type polymers, where we have this key phenylene unit in the polymer backbone that we can modify again synthetically, make it electron deficient, electron rich, to sort of tune the properties of the materials. And finally, we have this new class of isoindigo materials, where we can switch between P and N-type operations. So we can chemically modify these to either transport holes or electrons in a mixed conduction way. With that, I'd like to conclude. I'd like to thank all my group members who have contributed to this work. Also, my collaborators, Henning Seringhaus group in Cambridge, who do a lot of electrical characterization for us. Jonathan Ribney's group at Northwestern, who make a lot of OECT devices for us. And Professor Yoon's group in Gwangju Institute of Science and Technology in Korea, who also are doing OECT work for us. And thank you to all my funders who supported this work. And thank you very much for all of you for your attendance. It's been a pleasure. Thank you.